next speaker for this engineering session is presented by Dr. Leong Yin, which is my counterpart in the yin and the yang side. And he's
stuck in one place, but it truly is, like I said to you. Yeah, but don't cry, that's right. Now, on my talk this morning, I said that science said the #1 undiscovered scientific discovery is dark energy. And hopefully on my talk this morning, I gave you an answer what dark energy is. Well, the holy grail of clean energy, everyone should know, is fusion technology. Governments have not spent millions, not even spent billions, but probably spent trillions over the last 50, 60 years to develop fusion energy. You know, and all that money that they spent in 60 years, they've achieved absolutely nothing, which is they put energy in and they get less energy out. So, but they're still plowing millions and billions of dollars into that technology. Okay, so fusion is the holy grail of clean energy. Now, this title actually says an enormous amount within this little title. It's an intermediate fusion process. Okay? Intermediate in the sense of the temperature process. We all know about hot fusion, which is the simulation of the sun, which basically generates millions of degrees. And this is the technology that governments all around the world have spent so much money into, got so much and got absolutely nothing out of it. 10, 15 years ago, cold fusion came into our curriculum. There's still some debate whether cold fusion is or is not a real phenomenon. I think for the most part, most scientists believe cold fusion is a real phenomenon, but it is just as far away from being a producible end product as hot fusion. This intermediate fusion occurs at a few thousand degrees. So hot fusion, millions of degrees, cold fusion, hundreds of degrees, intermediate is a few thousand degrees. It is fully controllable. Now, I'm a nuclear physicist, so I worked on the old conventional nuclear reactor. And we all know what happened in Chernobyl and almost happened in 3 Mile Island. It can be very, very uncontrollable. And when it's very, very uncontrollable, it is a catastrophically failure. This is totally, totally controllable. And you'll see, obviously, in my slide just how controllable it is. And obviously, it is a nuclear fusion reactor. This is the next stage. You know, you ask the question, what is the technology to magnet gas? Well, this is the next stage from the production of magnet gas to the nuclear fusion process. So actually, I'll be going into a little bit of the physics of the production of magnet gas and this nuclear process. They're basically, well not basically, they are the same technology. You use the same mathematics, the same physics that have been developed by Professor Santilli. Okay, so now one important aspect that's not in this title, which is in the paper which I wrote, and is to be published soon, verification of intermediate nuclear fusion without harmful radiation. As I mentioned, I'm a nuclear physicist, so I know all about uncontrolled fusion reaction. Not only is it uncontrolled, but it produces a lot of radiation. Way, way too much radiation. See, here, this is one end of the electrode. There's a fixed electrode inside this chamber. This electrode is adjustable. Basically, the reason why it's adjustable is to maintain constant power input into the chamber. This is the power source that produces the electro arc between the positive and negative carbon electrode. Okay. Here's the gas manifold, which is attached to a vacuum pump, which is pumped out, and then high purity deuterium gas is injected into the chamber through these manifolds. You can see in this photograph one of the temperature sensors. We put one temperature sensor in the middle of the tube, and we put another sensor on one of the ends of the flanges, so we could characterize the thermal profile of this chamber precisely. This is a radiation detector that my company manufactured. It detects both gamma rays and neutron. We produce this for military application, for security, for geophysical surveying. So this has a very well proven technology, and I'll go into a bit more of it later on. And here's one of the magnet gas reactor there. So a little bit of physics, you know. First day was on the mathematics of the hydraulic mechanics. Second day was on the physics of it, and today is, like I said, on the engineering. So to answer your question, I'm basically backtracking to day 1 and 2. But I'm not a mathematician, like I said, I'm an experimental physicist. So basically the hydraulic mechanics is the only physics that can explain the neutron synthesis that can happen in stars. And Professor Santilli himself has actually verified this experimentally in the lab. And if you want, you can obviously get his paper, which is freely available online on a PDF. Okay, quantum mechanics cannot explain this. And that's why Professor Santilli had to develop his own math to explain, hey, what the hell's going on here? You know? Now, so this is for the neutron synthesis. Here is the production of the molecular, which is actually the form of magnet gas. I'm actually, or Professor Santilli is actually taking this process one step further. He's taking a step from just producing this magnet gas product, which as you've seen from the last two presenters, produces such a phenomenal clean gas. He's now going to the next stage, and he's creating fusion, the true holy grail of clean fuel. So to summarize, basically what happens is the electric arc produces an extremely strong magnetic field, on a very small radii. I think it's 10⁻12, if I recall. The field is phenomenally strong. Like I said, one of the problems with, the main problem that's obviously causing fusion is you've got electron clouds around the nuclei, and the electron clouds obviously repel each other, so they never get close enough for the nuclei to fuse together. Now in the sun, and in the billions of dollars that the government spends it, they just try to use brute force. Now the sun can use brute force because it's got enormous mass, enormous gravity to ram these nuclei together by sheer kinetic energy. Okay? Like I said, we don't want to use millions and millions of degrees to ram our nuclei together. So Professor Santilli, this hydraulic mechanics, explains that we produce an extremely strong field, localized field of the order of 10 to the power 12 Gauss. The Earth field is around half a Gauss, so we're talking about, you know, millions, more than a billion, 1,000 billion times stronger field than the Earth field. If you produce this localized strong field, you actually cause the electron cloud to go from a spherical shape into this toroidal shape. So these are two nuclei which has the electron cloud fully exposed because of the extremely high localized magnetic field produced by the electric arc. When this electron cloud is exposed like that, it attracts each other because of the polarity. So this ends up producing a molecular. I only show two atoms of this molecule, or molecular, but this can actually produce a long chain, which is what this magnet gas compound is made of. But for fusion, I only want to fuse two nuclei, so I represented here two nuclei. In the experiments I've done, as I mentioned, there will be a carbon and a deuterium nuclei that's been exposed and brought close enough together so that nuclei can basically fuse together to form a new element. So that is the math and the physics that we've been talking about today. So again, like I said to you, the math and physics is proven ultimately to work, and that's all that counts. You know, if it doesn't work, then hey. And like I said, quantum mechanics and the current math and the current physics cannot explain this. So a little bit more. So now the balance equation of this fusion process is given by this. I won't go through all these numbers and lettering. You can look it up in the textbook. But this is the reaction process from one nuclei, two nuclei forming the third nuclei. In our case, like I said, the one we were using was hydrogen 2, deuterium, was carbon to produce nitrogen. Now, to fully balance this equation, you need a trigger mechanism to cause these two to form the molecular cluster, to bring the two nuclei close enough together and cause fusion. Okay, so the trigger mechanism is that arc that produces that high voltage arc. So when you form the molecular cluster, the two nuclei, the two exposed nuclei come close enough together, they will fuse together to form the nitrogen plus, which is what you ultimately want, excess heat. Okay? So just to summarize, the electric arc triggers, polarizes the deuterium and carbon to form this molecular cluster. This is essentially a chain of, if you want to think it more traditionally, a chain of molecules. Okay? Now, we know from fusion experiment that when you fuse hydrogen with carbon, from the rest mass that you can calculate, you have an excess of mass, which is this. So when hydrogen and carbon form nitrogen, you got this amount of mass that is released, which obviously comes out as fusion energy. And for this amount of mass, it equates to just over 10 MeV of energy. Now, after we'd done the experiment, we did several runs. I didn't show the 50 psi one, I just showed the 100 and the 75 psi. One of the analysis that we did was we took samples of the gas in little cylinders before and after each reaction. These samples were sent to an independent lab, okay? It was not tested by Magnecular, it was not tested by my company. It was sent to an independent lab for full gas analysis. Now, there's reams of data. If you want to see the full data, I'll be more than happy to show you. It's in the paper that was published. But I just summarized some of the key components that was analyzed in this gas, okay? So basically, me and my team did two main experiments. We did one at 100 psi, so we pressurized the hydronic chamber at 100 psi of deuterium. This is the gas analysis before and after, and I repeated the experiment at 75 psi, again before and after. Okay, so before means I pumped out the chamber and then I inject it with this 99% pure deuterium. Okay, so the first line is this gas analysis of the deuterium. Second line is water, nitrogen, oxygen, and then mass higher than 50. Now, the reason why deuterium, the independent lab analyzed only 95%, of course, is the vacuum pump we used was a roughing pump. We didn't get down to 10 - 6, that we only need to rough it out. So that's why the measured content was, the bottle that we got was certified 99%. But we injected, there's still a small amount of residual air that was in there, and that's why the gas analysis came out with 95% deuterium in the sample, the reaction test. So you can see from this line that before each reaction, I just normalize this to 100% for the deuterium. After the reaction, there is a noticeable reduction in the deuterium. So obviously fusion did happen, and obviously the deuterium would fuse with the carbon and be eliminated from the gas analysis. So this obviously agrees with some reaction happening. The next line is water, again renormalized to before. As you can see, there's a large amount of water. Now, that's simply to explain. Everyone who ever works with a piece of metal or whatever knows the surface is highly contaminated with water. And when you heat this up to very high temperatures, the water is liberated. So this is not a chemical reaction, this is just natural outgassing from a surface whenever you heat it up. So any vacuum expert will tell you that's how you clean up the surface. You heat it up, you pump out the water. Okay? The nitrogen is what we're trying to create the fusion product. Okay? So you would expect the nitrogen initially, you intuitively say it should increase because you fuse, cause fusion, you're producing more nitrogen. So you say, well, there's an anomaly here. Why is the nitrogen, or the small amount of nitrogen that's present, actually reduced in one of the reactions? But remember, the process, one of the key process in this reaction is the formation of a long chain of molecules. Okay? It's a very complex long chain of molecules. So the nitrogen that created from fusion can actually be trapped within these long chains of molecular. Now, I will show you experimentally that we verified that this nitrogen was indeed trapped in these molecular. Okay? And that explains why in this reaction, a lot of the nitrogen was actually trapped within these solid molecular. And like I said, I'm going to give you experimental data to verify why this seems to go reverse to what you would expect. I can account for this nitrogen loss in this case. The oxygen content, in case where you say, well, is there any combustion? Well, there's a very, very small amount of oxygen there, too small to account for the generated heat, which I'm going to calculate later on. But just to show you, there is slight reduction in the oxygen. Well, I said the amount of combustion is nothing. It's more a few joules of energy that you get in the oxygen burning with carbon electrode. Okay? But this is very, very important, and you should take a note of this. I summarized this, the amount of molecules that have a mass higher than 50. In the original, before the reaction, there's a small amount of it. Now this could be due to the hydrocarbons from the pump backstreaming into the pump. Okay? But the most important thing is there's a very, very large increase in these high mass compound. Even more important than the percentage increase is the number of these higher mass element that appears. In fact, if you look at the spectrum mass of them, some of them cannot physically exist from standard physics. It just physically cannot exist. Like I looked at it, this mass cannot exist. Therefore, this must be the special long chain molecular. Okay, so this alone tells you these guys in Magnecular are creating something that is, present science cannot explain. But anyway, I just summarize it by clumping it all into anything larger than 50 mass unit. Obviously, if you want to look at the data more, I'd be more than happy to show you. But this is very, very important. So this is one major significant factor that we are, or Santilli's team is producing these long chain molecules, and also explain why this missing nitrogen is. And I've done another experiment to verify this nitrogen is indeed trapped in these molecules. Along with our company not only specializes in nuclear radiation detectors, we also manufacture X-ray detectors. So we did an X-ray microanalysis, which the team from Israel brought up your EDS process. This is an EDS, so when you mention EDS, hey, I know that, that's what we make. So EDS stands for Energy Dispersive Spectrometer. What does that mean? Basically, it is an identification system for identifying, in this case, solid element, elemental identification. That's what it's used for. I'll briefly describe what the instrument is, and I'll tell you then the significance of how this discovered that the nitrogen is indeed trapped in molecular. Okay, X-ray microanalysis works on this. Electron beam shoots down on a thin sample, Now this electron microscope, what it does is it just highly image the sample, but it doesn't tell you what the sample is. You look at it in a microscope and say, oh, that looks very pretty, but what is it? You don't know what it is. So what you can do, you can put in one of our radiation detectors, PGT manufactured radiation detector. This shows 2 versions. We actually manufacture 3 versions. This one's a liquid nitrogen version, which uses a silicon drip detector. And this one is a liquid nitrogen cool one, which uses a Santilli detector. So one of the things that happen when an electron beam hits the sample is the electron energy is absorbed and then it's re-emitted. So these electrons on these samples absorb, the electron shell jumps up and then they decay and then they emit their own signature X-ray. And that is the signature in the sense it has its fingerprint. Each element has a unique fingerprint. So by measuring its energy, you can tell precisely what the elements are. And that's why I asked you what the elements on your sample is, you know, internally, externally. So with this highly sophisticated equipment, you can identify precisely, accurately what solid samples are. So as part of the test is we took scraping of the carbon electrode. Okay? So this is a pure graphite, just like your Morpheus carbon that you use. It's just super pure, it's just carbon. After the reaction, we took some samples, scraped some, and we took it back to our facility in Princeton. And we put these samples into this EDS setup to detect if there's what is on the electrode. Now, if there's nothing on the electrode, it should be pure carbon. Okay? And I'm about to show you what we found. This is the spectral data that we observed. This is a fingerprint, the X-ray energy signature of all these elements. Of course, there's more element that goes down and down and down. So basically, in summary, the lighter the element, the lower the X-ray energy. Okay? So again, each one is unique. So by measuring the spectral energy, you can identify precisely what you have on that sample. The most prominent peak which identified was the carbon energy at 277 keV. Okay? So that verified that we were indeed looking at a carbon electrode. Now, if there was no fusion, no nothing going on, remember, this do not detect gas, so only solid entities can it identify. So with nothing else going on, the background should be absolutely flat. Okay? Now, you will notice this is not an anomaly. This isn't a peak. It was identified with our EDS. Okay? So this is a peak. What is this peak? If you looked at the energy of this peak, it is 392 keV. This is nitrogen. Therefore, that verifies that the nitrogen that was produced in the fusion, a large proportion of this was trapped on the sample. Okay? So that explains why in one of the samples the nitrogen appears in the gas analysis to be lower. Because of course that gas analysis, it was trapped on a molecular, as a solid molecular on the surface, then we verified that that is where the nitrogen was indeed trapped. And that explains for that experimental run why that nitrogen gas level was lower. The nitrogen was trapped in some form of molecular on the surface of the electrode. As you can see, we do not identify any other peaks on the sample. Okay, so this is the biggest, second biggest identification after the gas analysis that we were indeed creating nitrogen. So, now that convinced everyone that fusion happens, obviously one of the tests was that this fusion reaction produces no harmful radiation. Okay? Typical radiation nuclear plant produces copious amount of gamma rays, X-ray, neutron, proton, you name it, they spill it out. And that's why nuclear reactors you see on TV, they're so big. They're so big not because the reactors are actually big. The reactor's about the size of this room. But the building is, yeah, exactly. The building is like, oh my God, you know, a mile wide. That's because of all the shielding and they need to prevent that deadly radiation from coming out. And we've seen from Chernobyl, and we've almost seen with 3 Mile Island, what happened when you have a catastrophic failure and all that shielding goes. Chernobyl will probably be a toxic waste now for several thousands of years. I repeat, several thousands of years. That is what happened when you have an uncontrolled nuclear reaction. Okay? This is totally controlled. How can you stop it? Turn the arc off. It stops. Let the gas runs out. It stops. That's why this reaction is totally controllable. So anyway, this is one of the equipment that PGT brought with us. We manufactured it. This is our specialty. We're here to detect radiation. So the gamma ray is detected by sodium iodide scintillator. The crystals at the front of this detector is connected to a photomultiplier tube. So when an X-ray, not X-ray, in this case a gamma ray enters the scintillator, it produces light. The light is detected by a photomultiplier, amplified, and injected into this instrument, which will tell you what the gamma ray count rate is. Okay? Parallel to this gamma ray detector is a helium-3 detector, which does the same thing for neutron. Neutron is highly, highly penetrative. Okay? So that's another reason why the carbon deuterium was chosen as a reaction product. In this, like in molecular, you can inject sewage, you can inject anything. Well, for this fusion process, the beauty of this hydronic reaction is that you can actually start with almost a multitude of different elements and create nuclear fusion. For carbon deuterium was picked, and one of the aspects was you would produce no neutron, because neutron, like I said, is very, very penetrative. So this is the front of the screen that is on our detector. So it can detect the gamma ray count rate. So if it's in the red, it means run. Okay? If it's in the green, it means safe. If it's in the white, basically means, okay, there's absolutely nothing in there. Okay? It also gives you the count rate and the number of neutrons. This is the neutron count rate. And you see the background count rate, or not the back, this is actually measured with 0.03. It's actually the background. If you take this and isolate it, that is the background level. So you see the gamma ray below, even below the normal safety level. So again, background. So just to verify that we calibrated this radiation detector, it's very important, you know, you want to say, well, was the detector working when you took it there? Well, we tested it, we checked it at our factory, and we checked it when we got to the Institute of Basic Research. We checked the gamma ray detector. We actually calibrated it in our factory with a cobalt cesium radioactive source to make sure it's working. It has in it built-in a potassium-40 source. So therefore, in fact, this is the spectra. I don't really show it too clearly, but you see one black and one yellow. Black is the natural background that we measured before we did the reaction process, and the yellow is the measured spectra during the reaction process. And you see the two superimposed. So basically, there was no additional radiation beyond normal background radiation, which comes from cosmic rays, and even the steel radiates radiation. You measure that kind of levels. So basically, the measured level that we measured was way below the normal background level of less than 100 counts a second. Therefore, when we did the reaction, we verified absolutely that no gamma rays were produced outside the reaction chamber. Now, sodium iodide is actually spectroscopic, so it actually is more than just a counting device. You can also identify. In this case, for example, we identify our own self-calibrating radioactive potassium-40 source here, which you can see. So this is a deliberate source that we put in there to double check that our detector was actually working at all time. Okay? The helium detector, we could only calibrate it in our factory because this Californian source is very, very intense, you know, and it's not something that you can transport, etc. So we calibrated it in our factory with this source. So we had to store it in a huge steel vault, basically. So we calibrated to ensure that the detector was working, and then we took it to the facility. We did a background measurement of the facility before reaction. This was the background measurement, and we measured the system when the reaction was happening. And again, there was no change in the amount of levels. Therefore, no neutron was produced above normal background. So, the final thing is, okay, well, for it to be a working product, you better produce more energy than you put in. Otherwise, like I said to you, it's a not very good technology. But remember, this is a very small prototype, so it's not a working product as such yet. It's only a small prototype. So, as part of the test, as I mentioned, we put two sensors, one on the tube, on the center of the tube, and one on the end plate. And we measured the thermal profile. Time 0 represents when we start the initiation of the fusion process. In other words, we fired up the AC-DC converter. We actually could only fire up for 2 minutes because the amount of heat that was generated was way too much. It was reaching, as we were heating up the chamber, the pressure was going up in the chamber, and we had to stop the reaction because of safety issues. So we actually only initiate the fusion process for 2 minutes before we turned off the arc source to stop the fusion. So that's another reason why it's controlled. We continue to measure the temperature. Like I said, time 0, but we didn't just stop at 2 minutes, we kept measuring the temperature. So this is a thermal profile, measured thermal profile at the end plate, this black line. And this is the measured, again I repeat, measured thermal profile in the center of the tube. Then I contracted an independent company to do an FEA analysis. FEA stands for finite element analysis. It's basically a very sophisticated computer program that simulates the reaction, thermal, mechanical. In this case, I said, just wanted thermal. So again, I got the full report from them. If you want to see the full report, I'll be more than happy to go over it, but I'll summarize it in these two graphs. The company did a thermal profile, and they basically gave a profile at 5 megajoule, 5.5, 6 megajoule. So this bottom line is 5 megajoule, 5.5, 6 megajoule, and similarly 5.5, 6 megajoule of energy. The reason why this was picked was the watt meter that was connected to the power source, the AC-DC power source. For that 2 minutes, we measured it at 5.4 megajoule of energy being put into the chamber. So I repeat, for that 2 minutes, we only put in 5.4 megajoules, and this again was experimentally measured. So we know precisely how much energy we put into this reaction process. So therefore, if there's no other energy other than what we put into it, this measured profile should fit this middle red line. But as you can see, I'm sure you can convince yourself that our measurement shows clearly the thermal profile produced excess energy beyond what we put in. Okay, in both thermal profiles, this is much higher than this, although it does drop in here, but we're writing numbers out. It does show that it matches the outer profile, which is a 6 megajoule calculation. Therefore, the data that we produce shows that we produce at least 0.6 megajoules of excess energy. So I'm going to summarize here the whole experiment and our analysis. Okay? Well, I already gone through all the various analyses, which totally convincing that molecular fusion did occur. Okay? So how effective is this little prototype? Like, remember, this little prototype, this small. You know, so how effective was this nuclear fusion product? Well, as I told you, we measured 5.4 megajoules of input energy from an electric arc, which we injected for 2 minutes. The computer simulation clearly shows that we produce at least 6 megajoules of output energy. Therefore, luckily the math is simple. You take 6 from 5.4, you end up with 0.6 megajoules of excess energy. So I approximated. Therefore, the amount of excess energy that we produce from this process was half a megajoule. Right? So over the 2 minutes, that's equivalent to a 4 kilowatt generator. Okay? Which is pretty powerful considering the size that you have. Now, if you recall, for the deuterium-carbon process, for each nitrogen fusion, you generated around 10 MeV of nuclear fusion. Therefore, from this and this, I calculated that roughly 10 to the power 18, a micromole of nitrogen atoms was generated in this nuclear fusion process. And you said this may be large, but actually this is quite a small number. Remember, Avogadro's number is 10 to the power 23 of molecule in 1 liter. So yeah, this is only a very, very small amount of nitrogen fusion, yet it produces so much power from such a small reaction. Okay? Then I calculate, well, how efficient is that based on the amount of deuterium that we put into there? Well, I calculate that the amount of deuterium inside this chamber was roughly around 40 liters. Again, using a standard ideal gas, 40 liters, you should expect around 10 to the power 23, roughly a kilomole of deuterium atoms, okay, in this chamber. Therefore, from this 10 to the power 26 deuterium atoms, we form 10 to the power 18 nitrogen atoms. So the efficiency over this over this 1 minute period is roughly 10 minus 8. This is not a very efficient reactor. So despite it being not that highly efficient, we produce a sizable amount of excess energy. You know, so can we increase the efficiency? We have to increase the efficiency, you know. So obviously there are ways to increase the efficiency. One simple way is just to increase the operating condition, increase the pressure, increase the arc power, etc., etc. Other ways is have multiple arcs. Instead of one arc where you create the high field where the fusion occurs, have multiple arcs. So now you generate fusions all over the place. Another place is to flow the gas. So instead, again, to cause fusion, which causes a mini explosion nearby. So it actually prevents the deuterium from actually migrating to the arc, you know, for a momentary thing. So now you flow the gas, so when you create a fusion, the explosive kinetic energy is blown away by the gas, so you can see the process at a much faster rate. Therefore, there are actually, and like I said to you, Professor Santilli is actually building the next generation of nuclear hydronic reactor. He'll be more than happy to show you, which makes these processes a lot more efficient.
Thank you, Dr. Is there any question regarding this radiation proof?
Okay.
Yes.
Yeah, I have a question. You showed us how...
I did not physically make, but I said this was sent by independent lab. But remember, this is the same molecular and getting it to work. If it doesn't persist, it would not work. So that is my simple explanation.
Professor, we could not keep any longer than more than 2 minutes. So all the measures were stopped at after 2 minutes. After having said so, this I don't think we discussed it even among ourselves. Keep in mind that the nitrogen synthesis is not the only one. There are also a number of other syntheses. Only the other one are extremely small and certainly not even measurable. Some may be measurable in future tests. Incidentally, the nitrogen, you should know that the nitrogen, I selected the nitrogen. We tested this in many, many gases. But for the first paper, I selected the hydrogen to avoid unnecessary discussion with academic colleagues. Because if I had used another gas, oh, this could be this, oh, it could be this, oh, no, the heat, and then this endless discussion. With nitrogen was clear cut, all the fat out, because there was no combustion inside. As Professor Jonas correctly stated, no combustion. You have, in 2 minutes, you have such an excess heat that it cannot be other than nuclear fusion. One point also I want to clarify, the very fundamental point. We also selected nitrogen because, again, to cut out all the unnecessary discussion that damage the science and help nobody regarding the lack of radiation. Either the deuterium and the carbon, they fuse, 2 and 12 is 14, either they fuse or they don't. If they fuse, you cannot have no side radiation. Oh my God, otherwise, where they come from? Neutron. Because you should believe the last part of the 20th century, oh, unless there are neutron radiation, there is no fusion. My God, this is political beliefs with no fun, not even a shadow of scientific foundation. So either if you have the fusion, okay, then there is no possibility. Now, suppose you don't have the fusion. Ladies and gentlemen, there was a little electric generator, AC-DC converter. We lack 10 to the 14, where we miss 10 to the 14 MeV energy to smash. In other words, we have trillions of factors on the threshold energy to break the carbon nucleus, break the hydrogen, to make happy colleagues who are, oh, I have to wait for nuclear action. No, it's impossible to break it. We have an enormous margin of safety not to break any of those nuclei. It's been conceived in this way, to prevent any nuclear fission or radiation. And finally, the main conception is to start from light, not heavy. The opposite of what the scientific community has done to the 20th century. Start from light, natural, and stable element, light, natural, and stable element, and only consider fusion which are light, natural, and stable. Nitrogen is one of them. One final point, and then I apologize, because things are very exciting for me, I'm very tired. We should know that after the first paper, which is to conceive it on the nitrogen to prevent total unnecessary self-damaging and discussions in the damage science, we are working on a variety of gases, of course. One of the most promising you should know is CO2. We are working now very intensively to use CO2 to produce nuclear fusion, control the nuclear fusion without radiation. Because I'm an environmentalist, and it will take years, millions and millions of dollars to. Don't expect tomorrow morning a machine. It will be millions and millions of dollars to achieve any. I'm talking about fusion. It's talking about trillions of dollars we spend. We've spent so far. We spent thousands of dollars to achieve what. Well, not thousands, but we didn't spend the very enormous amount.
The beginning of the process, but you must think to replace this cylinder with hyperboloid with one sheet.
Oh yeah, no.
Because it's double ruled.
But the fusion occurs at the arc. At the arc.
Yes.
At the arc. Only at the arc.
Yeah.
From what we know, Professor,
Understand.
we could be wrong. It occurs at the arc. Very localized on the arc.
Okay. And your arc, electric arc, can be realized also using fractal circuits.
Yes, of course. Yes. And that
I have a little paper regarding these fractal circuits made with one of my PhD students. We didn't finish, but we have a lot of curious results regarding the magnetic field around such type of circuits.
Yeah. No, they made the cylinder because this is the easiest and cheapest and quickest way of making a cylinder. You get a TB weld, 2 flanges on, you're done. So that's the simple. So in a real working power station, will this be circular? Would this be a grid pattern? I should imagine so. You know, I don't think the reactor, the real size reactor, will be a cylinder. You know, in my opinion, I think it'd be some circular honeycomb structure where you have multiple arcs, gas flowing. It'll be a lot more sophisticated. This is a lot quicker, cheaper to manufacture.
Mentioned about, I mean, if you deuterium with the carbon-12, you are not going to produce any radioactivity. That's true. That's nuclear science, but stable the nitrogen-14 doesn't have any activity, nuclear activity there. So that's totally true. Now, I try to make 2 points in here. Now, you explained you're using a roughing pump, right? A roughing pump, you know how roughing pump works, right?
Oh yeah.
So what it does in the container, there's a scoop over there, there's no propeller. rotating it, turbine rotating it, moving the air out of your container, and then moving the air outside into the your container. So you can verify before you start the fusion. So what do? You just pour in the air, continues working, pumping out, okay? And then you blank test, gas analyze. What you done in gas analyze there, you sending an independent lab and measure how much nitrogen.
Well, this is basically what we did. I mean, as I said, we do measure some nitrogen. This is air, so there is already some nitrogen in there. So we're not. So I said to you, this roughing pump. Like I said to you, we inject a certified bottle, 99% of deuterium. Okay, so I can pump up with a high vacuum pump, which costs several down. I could obviously get to very, very low starting pressure. I could then inject the deuterium, and then this number will be close, very close to 99%. But I said to you, I roughed it out, the chamber, to medium pressure. The roughing pump will typically go down to about 0.1 millibar pressure, okay? So there is still some air in there, because it's not high vacuum, it's moderately rough vacuum, okay? And then I seal the thing off from the pump. Then I inject the pure 99% of deuterium into the chamber. And this is the gas analysis that came out, which is what I would expect. Pure deuterium with a little bit of tiny air, residual air. Like I said, the water is very simple to explain. You know, this is how people, I'm a vacuum expert, I've been doing it for 20 years. This is exactly what I would expect. When you heat something up, you boil the water. There's enormous amount of water on steel chamber. This is experimentally verified. I mean, these guys, Israel probably uses vacuum chamber. They're fully aware this is a natural occurrence. So the water is also easily explainable.
Thank you. Maybe a little more before and after. Also, in our test, with the original derivation was a little bit, of course, Professor Ying is much more, I'm not a nuclear physicist, it's immensely more sophisticated what I did initially. But what I did initially, after taking sample, I asked for a nuclear isotopic analysis, and the increase in nitrogen has been certified. Without, in other words, basically the nuclear isotopic penetrated without, inside those 470, those big clusters, identify the percentage of nitrogen everywhere.
Yeah.
And there was a clear increase of deuterium, increase of nitrogen has been certified by independent company.
And remember, this EDS do not measure nitrogen gas. I can pump full of nitrogen, it will not detect nitrogen gas. Well, first of all, we evacuate our scanning electron microscope 10-6. But even if I didn't have it, it would not detect. Our setup will only detect solid elemental component. This nitrogen is solid. Where does nitrogen come from? It can only come from one thing, this nuclear process. Okay? If this nuclear process did not happen, all I would see would be a pure carbon peak, which again, this shows an extremely high carbon peak. So this verified we were examining this correctly. We should see an enormous carbon peak, which is what this is. This is the graphite electrode, this is what we scraped off. So this again verified that something made this nitrogen solid. So yeah.
It increased to 130% by dropping the pressure to 75 psi. So my question is, do you recall what it was at 50 psi?
No,
Sorry, which one you say?
The nitrogen output.
we did not recall.
No, we don't. The reason why I did the 50 psi wasn't really. The reason why I didn't include the 51 is because I did not have a before 50. I should have bought it. What I did basically is I just ran it. I ran before, after, and then just for the hell of it, because I had a few hours before I need to jump to the airport, I did a quick run of 50 psi and did it after. I didn't do a gas analysis before, and that's why I didn't put this in, because I didn't have a comparison after, before.
Yeah, if I may say so. The primary interest is in the increase in pressure. That is because the efficiency apparently increases non-linear with increase in pressure. The real reactor should work at 3,000 psi.
Yeah.
So low pressure, we could care less. We have no interest in low pressure. Higher pressure, yes.
But clearly there was an increase dropping the pressure at 25 psi.
Yeah,
So
yes.
how do you explain that?
Which one?
Explain that?
Not in the production of nitrogen. No, not.
It says right there.
Which
So
one? This one?
No.
So no, compare the 75 psi to the 100 psi.
For what? Which element?
nitrogen.
Okay, so
So you have 130%.
no, these numbers are again normalized to the before reaction. So this 23 is relative to this 100, this 130 is relative to this 100. So in these reaction, you get what you're supposed to. There appears to be more nitrogen than when you started. Therefore, this is enough. But I said the molecular process forming these molecular chain is very complex. The last two presenters said to you, it is very complex. So how long are these chain? You really don't know. It's very complex. So in this gap, okay, the nitrogen that was caused by fusion remained in the gas. So the gas vapor showed up more nitrogen, which is what you should see. In fact, that's what I was expecting. In fact, I was shocked when I first looked at this. I was like, oh my God, this is, you know, where did this nitrogen go? You know, I'm like, this data. So just to tell you, Professor Santilli did not do this analysis. I did this analysis,
Yes.
okay, independently.
Oh, yes.
Okay, and that's why it took me several months to work through this analysis. But then, I was shocked by this. That's why I produced this data. Sure. But then, as a scientist, I said, all right, if fusion happened, where the blazes hell did this nitrogen go to? If I cannot find where this nitrogen is, this whole test could be completely invalid. So luckily, or not luckily, as a good physicist, I did an EDS experiment like them. And here, I should find only solid entities. And what popped up? Nitrogen. So then I was like, whoa, I'm relieved. I measured nitrogen. Okay, so now I can experimentally confirm why this dropped. For this sample, this dropped because the nitrogen was trapped in this molecular. Standard physics, standard math cannot explain this. I repeat, only hydronic mechanics.
But how do you
explains this
know that
formation.
in the 75 psi sample that there also wasn't nitrogen that was trapped as well? Did you analyze that one as well?
No, I only analyzed one of the electrode samples from the.
With the carbon. So that's where the carbon is, that penetrates, the nitrogen.
Is a relation between the compression of the hydrogen atom and the magnecules.
Repeat again the question.
At the beginning, yes, here, there is a relation between the compression of the hydrogen atom and the formation of magnecules.
Yeah. This
for the input and 6 for the output, yes?
this one or
So what are the uncertainties? Of
Sorry?
those, what are the uncertainties of those two values? You mentioned 5.4 plus minus what? 6.0 plus maybe.
well, yeah. I mean, obviously the FP analysis. I'll show you the data. I mean, I don't know what the uncertainty value in there.